Somewhere in Tennessee, a machine that costs $600 million and it can perform over a quintillion calculations every second just got outpaced by a chip smaller than your thumbnail, holding fewer atoms of information than a grain of salt has grains. That machine is called Frontier. It is one of the fastest supercomputers ever built. And in the summer of 2026, scientists at Oak Ridge National Laboratory quietly admitted something most people never expected to hear this decade. There is a class of problem their exascale machine cannot solve accurately, and a quantum computer just did. The problem isn't abstract, it's fuel. Specifically, it's the fuel needed to run a fusion reactor, the same reaction that powers the sun, the same reaction that scientists have chased for 70 years as the answer to clean, nearly limitless energy. And the strange part is that the breakthrough didn't come from a bigger reactor or a stronger magnet. It came from teaching a quantum computer to understand the chemistry of salt. Stick with this one, because by the end, you'll understand why some of the smartest engineers in American science just admitted their supercomputers hit a wall, and why the thing that got them past it might change how every future power plant on Earth gets built. Let's start with the fuel problem, because it's the part almost nobody outside the fusion world knows about. When people picture fusion energy, they usually picture two things slamming together and releasing a burst of energy, like a miniature star inside a metal donut called a tokamak. That part is true. Inside that donut, a superheated cloud of plasma made of two hydrogen isotopes, deuterium and tritium, gets squeezed by magnets until the atoms fuse into helium and release an enormous amount of energy. Deuterium is easy. It's pulled straight out of ocean water, and there's enough of it to last humanity thousands of years. Before we get to tritium, it helps to understand why fusion has been chased for so long. Fusion is the same process that powers every star in the sky, including our own. Unlike fission reactors, which split heavy atoms apart and leave behind radioactive waste lasting thousands of years, fusion fuses light atoms together and produces mostly helium with no meltdown risk, since the reaction stops the moment conditions aren't perfect. That's why fusion has been called the holy grail of energy for 70 years, and why it has also, famously, always been 10 years away. The physics was never the only obstacle. The engineering is just as brutal, and the tritium supply problem is one of the biggest reasons why. Tritium is the problem. Tritium barely exists in nature. It's radioactive, it decays fast, and today's entire global supply, built up slowly from nuclear fission reactors, amounts to only a few pounds a year. Here's the number that puts that in perspective. A single 1 gigawatt fusion power plant running at full output would burn through roughly a pound of tritium a day. That means the entire planet's current stockpile could keep one power plant running for only a matter of weeks before it ran dry. So, if fusion energy is ever going to work as an actual power source, and not just a laboratory experiment, every fusion reactor will need to make its own tritium while it runs. It can't rely on the outside world to supply it. And that's where the real engineering problem hides, tucked inside something engineers call a breeding blanket. Picture the fusion reactor's core wrapped in a thick liquid shell, roughly a meter deep, made of molten salt. Not table salt. This is a scalding, glowing liquid made of fluorine, lithium, and beryllium, held together in a compound researchers call Fly-B. When high-energy neutrons fly out of the fusion reaction, some of them slam into lithium atoms inside that molten blanket. That collision splits the lithium into helium and a brand new atom of tritium. The beryllium in the mix multiplies the number of loose neutrons flying around, so the blanket keeps making more tritium than it would otherwise. In theory, this blanket does 4 jobs at once. It breeds fuel, it shields the powerful magnets from radiation, it cools the wall facing the plasma, and it carries heat away to eventually spin a turbine. That's an extraordinary amount of work for one liquid to do. And whether it can actually do all 4 jobs depends on one tiny, brutal detail of chemistry that engineers have struggled with for decades. Here's the cliffhanger buried inside the chemistry. Once that fresh tritium atom is born inside the molten salt, it has 2 possible fates. Either it grabs onto a nearby fluorine atom and forms tritium fluoride, a corrosive, sticky compound that is a nightmare to extract and eats away at the reactor's internal components. Or it stays loose as a gas and simply bubbles up and out of the salt on its own, ready to be collected and reused as fuel. One of those outcomes builds a viable power plant. The other one corrodes it from the inside out. And for years, nobody could confidently predict which one would happen, because the tool scientists relied on to make that prediction wasn't precise enough to trust. That tool is called density functional theory, or DFT, and it's the workhorse of computational chemistry. Think of DFT as a shortcut for estimating how a molecule's electrons are arranged, without doing the impossibly complex full calculation of every single quantum interaction between them. It's fast, and for most chemistry problems, it's good enough. But molten salt chemistry isn't most chemistry. According to researchers at Oak Ridge, when DFT was applied to Fly-B, its estimate of the salt's free energy, the exact number that determines whether atoms bind together or drift apart, could be off by as much as 10%. That might sound small, but in this context, a 10% error is the difference between predicting a helpful gas and predicting a corrosive acid. It's simply not precise enough to build a real reactor around. So why can't a machine like Frontier just brute force its way to a better answer? This is where the analogy actually helps. Imagine trying to track the exact position and motion of every dancer in a packed stadium, where every dancer is also constantly influencing the moves of everyone near them. Now imagine that stadium isn't fixed. It keeps adding new dancers, and every added dancer multiplies the number of possible arrangements for the whole crowd. That's roughly what happens with the electrons in a molecule as it grows larger. The number of possible configurations doesn't just add up, it explodes. Even a machine that performs over a quintillion operations per second, which is what Frontier does, simply cannot chase down every possible arrangement in a system where the possibility space itself has grown too vast to search. Classical computers, no matter how fast, are still checking possibilities one path at a time, in a sense. And beyond a certain point, that stadium gets too full for any classical method to track, honestly. This is exactly the gap that quantum computers are built to close. A quantum computer doesn't check possibilities one at a time. It can represent many overlapping configurations simultaneously because the qubits at its core follow the same quantum rules that govern the electrons scientists are trying to simulate in the first place. In a very real sense, you're no longer approximating quantum behavior with classical logic. You're using quantum hardware to directly model quantum behavior. That's the theoretical promise quantum computing has carried for over a decade. The question was always whether it could actually deliver a useful, trustworthy answer on a real scientific problem, not just a toy example. In early July 2026, that question got a real answer. A team from Oak Ridge National Laboratory IBM and the Cleveland Clinic published new research, released publicly on the arXiv preprint server, showing the first known quantum computer calculation of the molecular chemistry inside Fly-B. They didn't simulate the entire meter-thick blanket. That's still far beyond what any computer, quantum, or classical can currently handle, since a full-scale blanket contains something on the order of a trillion particles. Instead, they pulled 9 smaller configurations out of their simulations, each one a cluster of 21 ions, and calculated the energy of each cluster both with and without tritium attached. Then came the real test. They checked their quantum results against the most demanding classical chemistry methods available, the gold standard techniques researchers trust when accuracy matters more than speed, and the quantum-derived numbers matched. Tom Beck, who leads science engagement for the National Center for Computational Sciences at Oak Ridge, put it simply. He said that when the project started roughly 5 months earlier, he did not expect to reach this point so soon. That single sentence is worth sitting with, because Beck isn't a marketing executive. He's a computational chemist who spent his career on classical supercomputers like Frontier, watching quantum computing promise breakthroughs that took years longer than expected to arrive. When someone in that position says the pace of progress genuinely surprised him, that's not hype. That's a scientist adjusting his own expectations in real time. But here's where the video needs to slow down, because this is exactly the kind of moment where headlines tend to run ahead of reality, and we're not going to do that here. This result did not solve fusion energy. It did not by itself produce a working reactor blanket. What it did was prove, for the first known time, that a quantum computer can match the best classical chemistry methods on a real, physically meaningful fusion material at a scale that matters for engineering decisions. That's a foundational proof of concept, not a finished product. The researchers themselves describe this as an early step, and they're already planning to scale far beyond the 21 ion clusters used in this first paper, aiming eventually to calculate the hundreds of configurations that a full free energy picture would require. So how did they actually pull this off, given that quantum computers today are still far from perfect, still prone to errors, and still limited in the number of qubits they can reliably use? The trick lay in how the researchers split the problem apart. They used a method called wave function-based embedding, which breaks one enormous unsolvable calculation into smaller, more manageable fragments called clusters. Think of it like translating an entire foreign language novel, not word by word across the whole book at once, but paragraph by paragraph, where each paragraph gets handled by whichever translator is best suited to it. Classical computers handled the simpler fragments, the paragraphs that don't need extreme precision. The quantum computer stepped in specifically for the fragments involving the most entanglement between atoms, the paragraphs where classical translation kept losing meaning. That quantum step used a specific technique called sample-based quantum diagonalization, which lets researchers sample from a quantum computer's output and reconstruct an accurate picture of the system's true energy state. Afterward, classical computers stitched all the fragments back together into one coherent answer. This exact hybrid approach, splitting a huge molecule into fragments and handling the hardest fragments on quantum hardware, wasn't invented for fusion first. Earlier in 2026, the same core team, led in part by Dr. Kenneth Mertz of the Cleveland Clinic, used this method to calculate the electronic structure of a protein made of over 12,000 atoms, in partnership with the Japanese research institute Riken and IBM. Beck credited that earlier protein work directly, saying that without it, the fusion salt clusters in this new paper would have simply been too large to fit onto today's quantum hardware at all. In other words, a breakthrough aimed at biology quietly became the key that unlocked a breakthrough in nuclear energy. That's the kind of cross-pollination that rarely makes headlines, but it's often how real scientific progress actually moves. Now here's the part of the story that points toward where all of this is really headed, and it's bigger than one salt calculation. The research team describes a long-term vision of a three-stage loop, where artificial intelligence, classical supercomputers, and quantum computers all work together continuously. In the first stage, AI agents sift through Oak Ridge's database of 70 years of molten salt research, proposing and screening candidate salt recipes automatically. In the second stage, the most promising candidates get modeled atom by atom on supercomputers using density functional theory, but since those simulations are expensive, the team trains AI stand-ins to approximate the physics fast enough to explore many more candidates than brute force methods would allow. In the third stage, exactly where DFT's accuracy runs out, the quantum computer takes over to nail down the precise chemistry of where the tritium actually ends up. Then the results loop back to sharpen the next round of AI-generated candidates, and the cycle repeats. Algeist, who serves as Chief Technology Officer of the Frontier Exascale Computing Project at Oak Ridge and co-authored this research, described the underlying challenge as one of the great unsolved optimization problems in engineering, because a real reactor blanket has to keep pulling tritium efficiently, even as its own chemistry shifts under constant neutron bombardment, extreme heat, and powerful magnetic fields. No single calculation, classical or quantum, can find the ideal answer to a problem that keeps changing shape while you're trying to solve it. That's precisely why the vision isn't quantum computers replacing supercomputers. It's CPUs, GPUs, and quantum processing units working as one coordinated system, each one covering the parts of the problem the others can't reach. It's worth being honest here too, because this field runs on optimism that doesn't always match the pace of reality. Quantum computing still faces real, unresolved engineering challenges. Today's quantum processors are what researchers call utility scale, not yet fault tolerant, meaning they still accumulate errors that limit how long a calculation can run before results become unreliable. Some experts remain cautious about how quickly these methods will scale far beyond 21 ion clusters, and reasonable scientists differ on how many years away a fully realized version of this AI quantum classical loop actually is. This is a genuine milestone, but it sits early on a much longer road, and the researchers themselves frame it that way. There's a bigger pattern worth noticing here too. This fusion result isn't an isolated event. It's one entry in a growing list of 2026 demonstrations where quantum computers, paired with classical supercomputers, tackled real scientific problems instead of laboratory toy examples, including simulating real magnetic materials, helping create a molecule with a never-before-seen half-Mobius structure, and modeling that 12,000 plus atom protein that made this fusion breakthrough possible in the first place. Quantum computing spent years being described as a technology that would eventually be useful. 2026 looks like the year that started to change, at least for specific, carefully chosen problems. To see how significant that is, it helps to know what Frontier actually is. It became operational in 2022 as the world's first verified exascale supercomputer, performing more than a quintillion calculations every second, and by mid-2026, it was still ranked among the fastest machines on the planet, purpose-built for exactly this kind of scientific simulation. That a 20-qubit quantum system, small enough to be called an early-stage research tool, could match that level of accuracy on this one chemistry problem says less about Frontier's limitations and more about how uniquely difficult this particular calculation is. It's not that classical supercomputers are falling behind across the board. It's that some problems, defined by the sheer number of ways electrons can arrange themselves, are simply the wrong shape for classical computing, no matter how much raw power you throw at them. And Oak Ridge isn't slowing down on the classical side either, which tells you a lot about where this is actually going. The lab isn't retiring Frontier or treating supercomputers as obsolete. It's building the next machine, called Discovery, designed from the ground up to combine high-performance computing, artificial intelligence, and quantum computing into a single integrated system, specifically aimed at breakthroughs in materials science, precision medicine, and nuclear fusion. The lesson Oak Ridge is drawing from this molten salt result isn't that quantum computers beat supercomputers. It's that some problems need both, working together, doing what each one does best. So where does that leave the actual dream of fusion power, the one that's been promised as 10 years away for the better part of 70 years? This result doesn't hand you a working power plant. What it hands you is something quieter, but arguably more important. A genuine proof that the hardest chemistry problem standing between us and a self-sustaining fusion reactor can now be modeled with a level of precision that classical computers, even the fastest ones humanity has ever built, could not reliably deliver on their own. Several experimental fusion reactors are already under construction around the world right now, racing toward that same finish line from different directions. This quantum result doesn't finish that race for them. It hands them a sharper set of tools for the hardest part of the course still ahead. And it does it years earlier than most people, including some of the researchers involved, expected it to arrive. If breakthroughs like this are the kind of thing you want to actually understand instead of just scroll past, that's exactly what this channel is built around. So consider subscribing so the next one finds you. Fusion has always been described as the energy source that's perpetually a decade away. What changed this July wasn't the reactor. It was the realization that the computer needed to design it might no longer be the bottleneck holding the whole thing back.